good morning and assalamu alaikum, my dear followers, subscribers, and ladies and gentlemen. I welcome you to this new video on stochastic frontier analysis involving estimation of production and cost functions. In this video, I'm going to explain the background, the theory, and estimation and interpretation of the stochastic frontier production and cost function analysis. Starting with a production frontier model, it can be written as yi, and that is equal to f of xi beta tei. In this function, yi is the output of the ith producer. There are n firms, I varies from 1 to capital N. Xi is the vector of inputs. There are m inputs in the production used by the ith producer. F of xi beta is the production frontier, and beta is the vector of technology parameters to be estimated. Let us suppose technical efficiency of the producer I can be written as a ratio of the observed output yi divided by f of xi beta, which is the optimal or the maximum feasible output. If technical efficiency is equal to 1, the observed or the actual output yi is equal to the potential or the maximum feasible output of f of xi beta. If technical efficiency is less than 1, it means there is a technical inefficiency in the sense that the observed output is below the maximum feasible output. That is, the actual output yi is less than the optimal or the potential output. The production frontier f of xi beta is deterministic, and it means that the entire shortfall of the observed output yi from the maximum feasible output f of xi beta is attributable to technical inefficiency. Such a specification ignores the producer's specific random shocks that are not under the control of the producer. To incorporate the fact that output can be affected by random shocks, that is random error, into the model, we have to specify the stochastic production frontier as follows. And the stochastic production frontier is given by yi, which is equal to f of xi beta e raised to the power vi times technical efficiency. In this stochastic production frontier function, f of x beta e raised to the power vi is the stochastic frontier, which consists of a deterministic part, and that deterministic part is f of xi beta, which is common to all producers, and a producer specific part e raised to the power vi, which captures the effect of random shocks to each producer. In order to explain it further, we may know that stochastic production frontier models were originally introduced by Egner, Lowell, and Schmidt in their 1977 paper, and by Muysen and Van den Broek in their 1977 paper as well. Since then, the stochastic frontier models have become a popular subfield or sub-branch in econometrics. Later on, Kumbaker and Lowell in 2000 provided a detailed introduction to the stochastic frontier production models. We can review the nature of the stochastic frontier problem as follows. Let us assume there is a producer who has a production function f of zi beta, where zi is the vector of inputs and beta is a vector of the technology parameters to be estimated in the model, as I mentioned this in the previous slide. In a world without inefficiency or error, the ith firm would produce qi, which is equal to f of zi beta. Stochastic frontier analysis assumes that each firm potentially produces less than the maximum possible output due to the degree of inefficiency. Thus, qi is equal to f of zi beta times xi I. where psi I is the measure of technical efficiency. So, as I mentioned, psi I is the level of efficiency from the ith firm. It must be in the interval of 0 and 1. If psi I is equal to 1, the firm actual or observed output is equal to the maximum or optimal output with the technology embodied in the production function f of zi beta. If psi I is less than 1, the firm is not producing the maximum feasible output, and it is not making the most of the inputs zi given the technology embodied in the production function f of zi beta. Because the output is assumed to be strictly positive, the degree of technical efficiency is assumed to be strictly positive as well. Output is also assumed to be subject to random shocks, implying that qi is given by f of zi beta xi e raised to the power vi. And in order to simplify it, we will take natural log on both sides of this function, and that will give us a natural log of qi, which is equal to natural log of f of zi beta plus natural log of xi I plus vi. If we assume that there are k inputs and that the production function is linear in logs, it defines ui is equal to minus natural log of xi I, and that yields the following stochastic frontier production function, which is given by natural log of qi, and that is equal to beta naught plus summation j varies from 1 to k beta j natural log of zji plus vi minus ui. Since ui is subtracted from the natural log of output, this restricts ui to be greater than or equal to 0, and it implies that 0 is less than psi I, which is less than or equal to 1 as specified above. As I mentioned earlier, Kumbaker and Lowell in their paper in 2000 provided a detailed version of the above derivation, and they showed that performing an analogous derivation in the dual cost function problem allows us to specify the stochastic frontier cost function as follows, and that is given by natural log of ci, and that is equal to beta naught plus beta q natural log of qi plus summation j varies from 1 to k beta j natural log of pji plus vi plus ui. In this stochastic cost function, qi is the output, zji are input quantities of inputs from j that varies from 1 to k. Ci is the cost of the ith producer or ith firm, and pji are the prices of the j inputs that varies from 1 to k. The efficiency effect is required to lower output or raise expenditure depending upon the specification of the function. The model that Frontier actually fits is of the following form: yi is equal to beta naught plus summation j varies from 1 to k beta j x ji plus vi minus sui, where s is equal to 1 for the production functions and it is equal to minus 1 for cost functions. So, in the cost of the discussion above, yi is equal to natural log of qi and xji are equal to natural log of zji for the production function, and for the cost function yi is equal to natural log of ci and xji are the natural log of pji and natural log of qi. We must take the natural log of the data before fitting a stochastic frontier production or frontier cost model, and the command frontier performs no transformations on the data. It means that the frontier command does not perform any transformation on the data. Different specifications of the ui and vi terms give rise to distinct models. The frontier command in Stata provides estimation for the parameters of three basic models in which idiosyncratic component Vi is assumed to be independently normally distributed with zero mean and variance sigma square V distributed over the observations. The basic models differ in their specification of the inefficiency term Ui as follows. Ui may follow exponential distribution, and in that case Ui's are independently exponentially distributed with the variance sigma square U. Ui are also maybe half normally distributed with the zero mean and variance sigma square U, or Ui are independently normally distributed with the constant mean mu and variance sigma square distributed with the truncation point at 0. For the half normal or exponential distributions, the command frontier in Stata can fit models with the heteroscedastic error components conditional on a set of covariates. For a truncated normal distribution, frontier can also fit a conditional mean model in which the mean is modeled as a linear combination of a set of covariates. As I mentioned, the frontier command in Stata can fit stochastic production or cast frontier models, but the default is a production frontier model, and it provides estimators for the parameters of a linear model with a disturbance that is used to be a mixture of two components which have a strictly non-negative and symmetric distribution respectively. That is, one component is normally distributed with zero mean and constant variance, and the other component is strictly non-negative. That may be exponentially distributed or half normally distributed or truncated. Frontier can also fit models in which non-negative distribution component, which is a measure of inefficiency, is assumed to be from a half normal, exponential or truncated normal distribution. Later on, we will estimate all these three models, that is half normal, exponential and truncated normal distribution models. In this video lecture, the data is from the transportation equipment manufacturing industry from USA, and we have observations on the value added, the capital and labor which are used to estimate a Cobb-Douglas production function, and the variables in this data set is the natural log of value added, that is log transformed value added, natural log of capital, which is a log transformed capital, and natural log of labor is the log transformed labor input. OLS estimates are given, and they are compared with those of the stochastic frontier production models using both the half normal and exponential distribution for the inefficiency term. Later on, models with heteroscedasticity and the truncated normal model will also be estimated for comparison with those that are mentioned above. So, after this introduction of the background and the theory of stochastic frontier production and cast models, we are now in a position to estimate some of these models in Stata. And to do that, I'll open my data file in Stata. Here is the file which I have already opened. First of all, I will show you the data. This is data. This is sorry, let me show you the other file that is not the relevant one. First of all, I'll clear this file, and I use this data from the William H. Green book, and here is the original file. I'll show this. This is a state-wise data from USA, starting from Alabama, California, Connecticut, Florida, Georgia, Illinois up to Wisconsin. There are 25 states. The second variable in this data set is value added. Then we have capital, labor, Number of firms, there are 68 firms from Alabama, 1372 firms from California, and so on. Then we have log transformed value added, log transformed capital, and log transformed labor. So this is the data. We will first use this data set. The starting point is that first of all, I would like to estimate the OLS model, in which the log transform value added is regressed on log transform capital and log transform labor with the regress command. And here is the estimated model. This is the analysis of variance. This is model sum of square or regression sum of square. This is residual sum of square or unexplained sum of square. This is total sum of square. And here we have model level statistics. Total number of observations given are 25. This is F statistic value. This is P value of the F test, and this is R squared value. This is adjusted R squared value. This is root mean square error of the residual. These are the coefficients of log transformed capital, and this is significant at 5%, and this is the coefficient of log transformed labor, which is highly statistically significant, and this is the constant term of the model, and this is the starting point. So after this, I'll estimate the frontier production model, in which the log transform value added is regressed on log transform capital and log transform labor. And here is the estimation of this model. So this is half normal model. Number of observation 25. This is Wald chi-square statistic. This is the p value, and these are the coefficients of log transformed capital, log transformed labor, and this is a constant. So we may compare the coefficient. This coefficient for the log transformed capital is 0.258, whereas the corresponding coefficient for the log transformed capital in the OLS model is 0.245, and for OLS model, the log transformed coefficient for the log transformed labor is 0.805, and in the half normal model it is 0.780. So there is a little bit of a difference between the coefficients of the two model, but both the coefficients are significant. There are some other statistics like natural log of sigma square v and natural log of sigma square u, sigma v, sigma u, sigma 2, and lambda. I'll explain these later on. After this, I'll estimate another model with exponential distribution. So the first one was a half normal model, and now we have the exponentially distributed model, and this is the output of the exponential model. Again, these are the number of observations. This is Wald chi-square. This is p value, and these are the coefficients of log transformed capital and log transformed labor. This is the constant. Again, there are those statistics that I'll explain later on. This is a log likelihood ratio test of sigma u equal to 0. I'll explain this in a while. This is how we predict residual for this model. So the residuals have been generated, and let me show this to you. So this is the newly generated residual for this model. After this, so the conclusion of these three models, that is the OLS, the half normal model, and the exponential model, is that although there is some difference in the numerical values of the coefficients of the log transformed capital and log transformed labor, but both the coefficients are significant in the three models, and the only difference is that one is OLS model, the other one is half normal model, and the third one is the exponential model. After this, I will use a model with heteroscedasticity. So I will clear this file, this data file, and I'm going to show how to estimate models with heteroscedasticity. So my topic is models with heteroscedasticity, and for that I will open another model, another data set, which is given by Frontier 1, and this is my data file, the second data file, for which I'll estimate models with heteroscedasticity. And we assume that the the variance, the residuals depends upon the size of the firm. So in this file we have size of the firm. This is the log transform labor, log transform capital, and log transform output. So let me close this, and I would like to estimate the frontier, the stochastic frontier production model, where the residual or the inefficiency depends upon this size of the firm. So this is the estimated model where where the variance depends upon the size of the firm, and these are the coefficients of the number of observations for this model is 756. This is what chi-square, and this is a p-value of the chi-square, highly significant. This is the coefficient for the log transformed labor, which is equal to 0.709, and this is the coefficient for log transformed capital. This coefficient is not significant, whereas this coefficient for the log transformed labor is significant, and this is how log square V depends upon the size of the firm, and there is negative sign. There is a natural log of sigma square u for the consumption, and we have sigma u here. After this, I'll run this test, and this test basically means that the coefficient of labor and that of the capital, if we sum them up, then they are equal to 0. So it means that we are going to test the hypothesis that there is constant return to scan in the technology, and this chi-square test p-value is more than or greater than 0.05. So we fail to reject this hypothesis. So we conclude that there are constant return to scale technology, and this output indicate that the variance of the idiosyncratic error term is a function of the firm size. And also we fail to reject the hypothesis that the firms use a constant returns to scale technology that I mentioned earlier. After this, I'll clear this because I'm going to use another set of data for the truncated normal model. So now my topic is the truncated normal model, and I will use another file which is given by Frontier 2, and here is my data. And this time let me show you the data. We have quality, we have some qualitative variable here, and this is the natural log of the price of capital, this is the natural log of price of labor, this is the natural log of output, and this is the natural log of cost. So here now I am going to estimate the stochastic frontier cost function for these firms. So here is and that is truncated model. So my stochastic frontier cost model is being regressed, but I'm using truncated normal cost model. So this is the output of this model. There are iterations. This is truncated normal model. Total number of observations 1231. This is Wald chi-square. This is its p-value. This is log likelihood. These are the coefficients of log transformed price of capital, log transformed price of labor, log transformed output. This is constant, and in this model two of the coefficients, that is log transformed price of capital and log transformed price of labor, are statistically insignificant, and the log transformed output is significant at 5%. There are some other values like mu, natural log of sigma 2, this is the logit of gamma, sigma 2, gamma 2, and so on. I'll explain this. So to do that, let me go to my PowerPoint slides, and here in this slide, as I mentioned earlier, We have OLS model here. This is the half normal model here, and this is the exponential model here, and we have already compared these coefficients. So after that, I'll expand some of the output of this model. The output from the frontier stochastic frontier production model includes estimates of the standard deviations of the two error components, that is sigma v and sigma u, which are labeled sigma sub v, sigma sub u respectively. In the log likelihood, they are parameterized as natural log of sigma square v and natural log of sigma square u, and these estimators are labeled as slash natural log of sigma 2v and slash natural log of sigma 2u in the output. Frontier also reports to other useful parameterizations the estimate of the total error variance sigma square s, and that is equal to sigma square v plus sigma square u, and it is labeled as sigma 2. So sigma 2 in the estimated model stands for sigma square s, and that is the estimate of the total error variance. And the estimate of the ratio of the standard deviation of the inefficiency component to the standard deviation of the idiosyncratic component lambda is equal to sigma square u divided by sigma square v, and this is labeled as lambda. At the bottom of the output, Frontier reports the result of a test that there is no technical inefficiency component in the model, and this is a test of the null hypothesis h naught sigma square u is 0 against the alternative h naught sigma square is greater than 0. If the null is true, the stochastic frontier model reduces to an OLS model with normal errors. However, because the test lies on the boundary of the parameter space of sigma square u, the standard likelihood ratio test is not valid, and a one-sided generalized likelihood ratio test must be conducted. For this example, in the output above, the output shows LR is equal to 0.43 with a p-value of 0.256 for the half normal model, and log likelihood ratio equals 1.21 with a p-value of 0.135 for the exponential model. There are several possible reasons for the failure to reject the null hypothesis, but the fact the test is based on asymptotic distribution and the sample size was 25 is certainly a leading candidate among those possible. So it means in both the model, on the basis of the test, we reject the null hypothesis that there is no efficiency. After this, I'm going to show the another model that I estimated in the Stata, and this is the stochastic frontier cast model, which is with truncated model. In addition to the coefficients, the output reports the estimate for several parameters, that is sigma v square, this one sigma v square, which is the estimate of sigma square v, and sigma u square, which is the estimate of sigma square u. Gamma is the estimated estimate of the this gamma, which is equal to sigma square u divided by sigma square s, and that is sigma 2 is the estimate of sigma square s, which is equal to sigma square u sigma square y plus sigma square u. Because gamma must be between 0 and 1, the optimization is parameterized in terms of the inverse of the logit of gamma. So that is why it is given by ILGT gamma, that is inverse logit gamma, logit of gamma, and this estimate is reported as ILGT gamma because sigma square s must be positive, and the optimization is parameterized in terms of the natural log of sigma square s, whose estimate is reported as natural log of sigma 2, and this is natural log of sigma 2. Finally, mu is the estimate of mean mu of the truncated normal distribution. So this is truncated normal distribution model. In the output above, the generalized log likelihood test for the presence of the inefficiency term has been replaced with a test based on the third moment of the OLS residuals. When mu is equal to 0 and sigma square u is equal to 0, the truncated normal model reduces to a linear regression model with normally distributed errors. However, the distribution of the test statistic under the null hypothesis is not well established because it becomes impossible to evaluate the log likelihood as sigma square u approaches 0, prohibiting the use of the likelihood ratio test. However, Coyley in his 1995 study noted that the presence of the inefficiency term would negatively skew the residuals from NOLS regression. By identifying negative skewness in the residuals with the presence of inefficiency term, he derived a one-sided test for the presence of the inefficiency term, and the result of this test are given at the bottom of the output here in this. And for this example, the null hypothesis of no inefficiency component is rejected, which means that there is inefficiency present in this estimation. In the above example, in the below example, we fit a truncated model and detect a statistically significant inefficiency term in the model. We might question whether the inefficiency term is identically distributed over all forms of R, whether there might be heterogeneity across the form. Frontier provides an extension to be truncated normal model by allowing the mean of the inefficiency term to be modeled as a linear function of a set of covariates. In our data set, we have categorical variable and that measures the quality of a firm's management. We refit the model including the CM option, that is conditional mean, specifying a set of binary indicators variables representing the different categories of the quality measurement variable as covariates. And here is the estimated output of stochastic frontier cast model, which is truncated normal, and we have the conditional mean of the quality. So since there are 5 categories, so one is taken as the base category. These are the coefficients of the model, of the cast model. This is the coefficient of the log transform price of capital, which is insignificant. Then we have coefficient of the log transform price of labor, that is also insignificant, and the coefficient for the log transformed output is significant. And then we have coefficient for the various categories, and except this one, all other coefficients are insignificant. And finally, we have these parameters as explained earlier. The conditional mean model is developed in the context of panel data estimators, and we can apply Frontier's conditional mean model to panel data also. So this is a detailed discussion, explanation of the stochastic frontier cast models involving OLS, half normal, exponential model, and truncated normal model for the cast also, and then models with heteroscedasticity and their interpretation. I hope this is quite new for many of you, and I hope you like it. If you like it, kindly subscribe to the channel and do not forget to click on the bell icon so that you could get timely notification about my other videos that will be uploaded for you. Thanks for watching this video. Kindly share this channel and various videos of this channel in various WhatsApp groups so that these could reach to the maximum possible number of people. Thank you, and see you in another video soon. Goodbye.